Welcome to the second part of the podcast. We are now here in Professor Zaccolo's lab in the Department of Physiology, Anatomy and Genetics in the University of Oxford, and you are going to watch a real Fred experiment by her team. Andreas will introduce us the team.
Okay, these are my colleagues Donna, Nchuge, Marcella, Nicoletta and Stefania. Hi. After Manuela had told you in the first part of our podcast the main facts about Fred and what you can do with it, I will give you now some guideline on how to perform a sensitized Fred imaging experiment. This method does not require particularly sophisticated equipment and can be used by any laboratory. In general, it's perfectly adequate to measure dynamic Fred changes in cultured living cells. In this podcast, we will lead you through the general setup of a Fred imaging system, how to prepare cells for a Fred experiment, and the measurement itself with the basic acquisition setup, and the analysis of a Fred experiment. So here you see our Fred equipment, one of our Fred equipments, with the lamp in the background, the microscope with some really good objectives, the beam splitter and the camera.
Here in this simplified scheme you can see all the components I just mentioned. In our case, the light source is a powerful light-emitting diode. The light of this LED is filtered to the adequate excitation wavelength through an excitation filter and reflected to the cells. The combined emissions of both fluorophores are then collected through the objective lens. As they have longer wavelength, they can now pass through the selective so-called dichroic mirror. Then they are reflected to the beam splitter. By passing through the dichroic mirror and the filters in this device, the previously combined emissions are separated into the yellow and cyan emissions, which then are reflected by other mirrors to separate parts of the light-sensitive chip in the camera. This chip converts the image pixel by pixel into fluorescence intensity values, which then can be converted into storable data and are visualized online on the screen. Here the original grayscale images are shown in yellow and cyan for the respective wavelength and in pseudo-color for the calculated ratio image. To control image acquisition, visualization and analysis, most of the major microscope manufacturers provide their own customized imaging suites. However, there are also some freeware solutions available. As we are using Metamorph and Metafluor, two programs which are quite commonly used and suitable for most setups, I will show you the essential steps to set up a Fred experiment and its analysis with the Metafluor program. At the first start, you will have to check and specify some general parameters. First, make sure that your system is configured to use a beam splitter, here called Dual View. Then start your experiment by clicking the New Experiment button. Go to the Configure Experiment dialog. Tick the boxes for wavelength 1, 2 and the ratio. Make sure that also these boxes are ticked. If you now return to the main program interface, you will see that three windows appeared, which later will show the emission images for the yellow and the cyan channel and the ratio image. Now we will have to set up the camera. Most imaging cameras do have an option for binning. Binning means that the number of adjacent light sensor pixels on the camera chip are virtually summed up to one superpixel. This enhances the signal intensity but decreases the spatial resolution. Here we use binning 1, meaning we use the full resolution of the camera chip. A binning of 2 would give you roughly a fourfold increase in the signal intensity but reduces the resolution by half. Higher binning would further increase the signal strength, but also further decrease the resolution. Another parameter that influences the signal intensity is the camera gain. You can reach this option in the Configure Acquisition menu. As gain means an electronic amplification of the initial signal, a higher gain typically will enhance your signal, but will also introduce a certain amount of additional noise. For our experiments, we usually select a total gain of 1, which means no additional electronic amplification of the signal. As you will realize also with other parameters, it's always kind of a trade-off. Here you will have to find a compromise between signal intensity, spatial resolution and background noise that is the most appropriate for your sample. The same is true for the illumination intensity and acquisition time. You can enhance a weak signal by increasing the illumination intensity and acquisition time, but this might bleach the sensor or stress your cells excessively. The illumination time is set in the Configure Acquisition menu. A good starting point is an illumination time of 100 to 200 milliseconds. The intensity has to be set by a hardware control knob at the LED power supply. We usually work in a range between 1 and 3 watt LED input power. The last parameter to set is the sample interval. This also very much depends on the temporal resolution you need, the photostability of your sensor, and the resistance to phototoxicity of your cells. As the kinetics of cyclic nucleotide changes are comparably slow, a sampling interval of 5 to 10 seconds mostly is sufficient. However, in case you would be interested in faster kinetics, you could increase the temporal resolution by increasing the sampling interval. The last point in this menu is the number of acquisitions. As you can stop the acquisition at any time, just select the number you will usually not exceed. After all basic parameters are set, store them with the Save Parameter dialog. I will show you how to do it later, as we will now first have a look on how to prepare the cells. As we have to seat the cells on glass cover slips, we first have to sterilize these cover slips. Here Stefania simply dips them for a moment into an ether ethanol or 70% ethanol water mix. Then she lets them dry for a couple of minutes. Many cells do not require a specific coating, but as we intend to seed cardiac myocytes on the cover slips, we also have to previously coat them with a 20 microgram per milliliter solution of laminin and PBS. We usually apply 250 microliter of this solution onto each cover slip and leave them in the incubator for about 2 hours. Before seeding the cells, aspirate this solution. In our experience, seeding about 600,000 myocytes per well yields good results. Then put the cells back into the incubator and let them settle down for about 24 hours. After this period, the cells are ready for transfection with your FRET sensor using the transfection protocol of your choice. After adding the transfection mix to the cells, it usually takes another 24 hours in the incubator until they express the sensor adequately. Typically, we measure the cells 24 to 48 hours after transfection. To start your experiment, prepare the cells for the measurement and start the program. Then select your saved protocol. Just click OK for this dialog. Then select New to create a new experiment. As until the latest version, there's a program bug which otherwise leads to some inconvenience when replaying the saved experiment, make sure that all thresholds are set to off. If you deliberately want the threshold, it is better to do so during an analysis session. Thresholds can be set either in the display menu or with a button and the sliders on the left control bar of each wavelength window. We recommend to do it first with the menu, then close the menu and do it again in the bar. There's also an issue with some image processing. As I will show you later, the program can do background subtraction. However, if you do so during acquisition, the software will save the processed data instead of the raw data. Your original data will be lost, so better refrain from any processing during acquisition. To start the experiment, switch the microscope light path to the camera. Then start the focusing mode of the program. Focusing mode lets you see your cells in a live mode. Depending on which illumination and filter mode you choose, you can see bright field images or YFP and CFP emission images on the left and on the right half of the screen. You can use that mode to look for cells or to position your cells optimally in the field of view and to focus. However, be aware that if you do this in fluorescence mode, the cells are illuminated all the time, which will considerably stress them and might bleach the sensor. Therefore, it's better to look for the cells directly through the eyepieces and to focus only after you found a cell suitable for your experimental question. You should not use cells which are very bright or cells which are extremely dim. To narrow down variations, try to always use cells comparably in morphology and fluorescence intensity. Focusing mode can also be used to quickly identify the allocation of the wavelength images to the real emissions. As this allocation depends on the orientation of the camera chip and can be different in different setups, you may want to check this. The left part of the camera chip in metafluor always is assumed to harvest the yellow emission and is named as wavelength 1. As here in the focusing mode, I excited only with the yellow excitation wavelength and the emission image can be seen at the left half of the image, the allocation is as expected by the program. Now go back to the main program. Acquire a first image of the cells and check for the emission intensity. The quickest way is just to hover with the mouse over your cells. In this little field here you will see some numbers changing. The last number represents the actual brightness. The value for the cells here is up to 2000 and around 190 to 200 for the background. I mentioned before that imaging always is a compromise between temporal and spatial resolution versus signal-to-noise ratio and sensor or cell damage. Therefore, you should go for the lowest illumination settings that still make sense for your requirements. In our setups, the signal should be at least twice or 3 times the value of the background. But a signal exceeding about 1000 gray values is not absolutely necessary. As most of the cells here have a strong signal, we may actually decrease either the illumination intensity or the illumination time to minimize sensor bleaching and phototoxicity. Go to Configure Acquisition, try 200 milliseconds and acquire the next image. This time the emissions all are in the range from 500 to 1200 gray values, which is absolutely fine. However, if you know your cells and sensors would tolerate it, you could go massively up with the illumination time or power. The program will show you how close you are to saturate your camera chip. This little white graphic here at the sidebar shows you the distribution of gray values for your image. As long as it doesn't reach the top, the signal isn't saturating the camera chip and everything is fine. You will have noticed that some of the cells in the ratio image show strange color fringes. This is due to a mismatch of the pixel of the YFP and the CFP image. They are not optimally superimposed or so-called misaligned. Usually you should hardware align your beam splitter every now and then to avoid this. However, as long as the misalignment is only a few pixels, you can also do a software alignment during the experiment or better when you analyze the experiment offline. I will show this later. You will see that there will always remain some misaligned areas. This is due to issues with the beam splitter I'm using. Unfortunately, nearly all available beam splitters show such imperfections. Here you see some common issues: rotated images, size mismatches, general distortions, and even focal plane aberrations. Of all of our beam splitters, the beam splitter you have seen in the overview of the other setup before shows the least distortions, and there is even a further improved version now available. In my setup, I try to keep the central area best possibly aligned. In case I have to analyze also other parts of the image, I can just apply the adequate software alignment during offline analysis and run a second analysis. If you would like to software align your images already at acquisition, you may now tick Align after acquisition, which then applies the alignment to all further acquisitions. However, I tend to rather accept small misalignments during acquisition than to store already processed data. Anyway, the final analysis will be done offline. Therefore, I usually untick this option and do it only during playback. Next, you should set the display mode and range for the ratio image. This ratio image is created by dividing the value of the yellow emission intensity by the value of the cyan emission intensity for every corresponding pixel of the images. The ratio value is then initially expressed as a gray value on the ratio image. As the human eye can only distinguish about 60 to 100 gray values, we preferentially use pseudo-colored representations, which give better distinguishable differences even for small ratio differences. In addition to the simple pseudo-color, Metafluor has also an intensity-modulated display mode. These display modes are only for a visual representation of what's happening during the experiment. They will in no way change your original data. Feel free to play around with the parameters so that you have the best possible representation of your experiment. Once you found the scaling that works for your conditions, you should keep it, as it gives you immediately an idea about the state of your cells. In our case, we transfected the cells with a loss of FRET CAMP sensor, which works quite similar to the well-known EPAC1 CAMP sensor. Just to remind you, this animation shows you how these sensors work. Upon binding of CAMP, the molecule changes its conformation, which leads to a change of the distance between two fluorophores, and consequently to a change in the efficiency of the energy transfer between them. As you can see, with this sensor we expect the ratio of the yellow emission intensity divided by the cyan emission intensity to go down with increasing CAMP concentrations. As I know already that for this sensor we may expect a basal ratio of around 2, I will set the maximum to just above 2, and the minimum to about 0.5. This means that a ratio value of 2.2 will be allocated to red, and the lowest expected ratio, which indicates the highest measurable CAMP concentration, will be shown in deep blue. The values in between are allocated to the other colors of the spectrum. The last thing I will show you before we start with the experiment is how to draw regions of interest, the so-called ROIs, which will be used to extract the numerical average emission intensities of the cells or part of the cells you are interested in. Go to the Regions dialog by pressing the button and confirm that you would like to draw the regions on the ratio image. Although we will draw there, the region is valid for all wavelengths. Drag the window to a convenient place and maximize it to your preferred size. You can either drag the corner, click into the image and use the mouse wheel, or use the magnification button. Press it and open a rectangle over your region of interest by right-clicking and dragging. If you magnify it too much, just use the mouse wheel to get back to a lower magnification. To see the cells better, you can also increase the brightness of the picture with the slider at the side. Now open the Region tool by pressing the respective button. I always use region 1 as the background region. Therefore I can now create the first region by using the rectangle or ellipse tool. Make sure that this area in fact contains only background. Click on the area, then click and drag to increase or decrease the size of the ROI. Create some more regions on the cells. These are just for the preliminary online analysis, therefore they must not be very precise. However, if you would like to outline the shape of a cell more accurately, you could also use the Polygon tool. Close the shape by double-click. If you activate the Select tool, you can move regions by clicking into them and drag them, or you can modify the shape of a region by clicking on the line. Click Done to get back to the main program. You may now already have some graphs. If not, you will have to configure the graphs. Click on the Graph menu. In my case, I have them already configured. The average intensity of wavelength 1, which in my setup corresponds to the yellow emission, should be shown in solid on graph 1. Wavelength 2, the cyan emission, should be dotted. The ratio should show up on graph 2. You can customize all these settings. Make sure that this box is ticked to show the respective graph. You can access some more graph options just by right-click on the graph. Click Close to return. Your setup is finished and you may want to save it as a protocol, so that the next time you can just load this protocol and you are ready to go. Go to File, Save Protocol File. Give some description, then press Save. In the next dialog, save it with a meaningful name. Finally, you should not forget to save your experimental data. Go to the Experiment Control panel and tick Save Images. In the pop-up window, navigate to the folder where the experiment should be saved. Again, save it with a meaningful name. Then click Save. The two now green enlightened small boxes indicate that the wavelength images 1 and 2, in our setup yellow and cyan, will be stored now. It's not necessary to also store ratio images or to log data, as these will always be recalculated when replaying a saved experiment. Until now I have shown you all the setup procedures with the CHO clone transfected with a CAMP sensor. For the sample experiment, we will now return to the transfected cardiomyocytes my colleagues prepared for this movie 48 hours ago. Here you see Nicoletta preparing the cells for the measurement. First she mounts the cover slip into the bath chamber. For this experiment we use a simple metal chamber which is perfectly fine for many standard experiments. As the cells are kept in a Heaps buffered modified tyrrhate solution, many standard experiments can still be done just at ambient conditions. This simplifies the setup. However, if experiments require more physiologic conditions, you will have to use a bicarbonate buffered solution and to apply environmental control. This can be done by using temperature and gas controlled chambers. Now Nicoletta will have to look for a suitable cell, do the initial adjustments I explained before, and then she will start the experiment. As this would take too long in real time, we have a time-lapse video of exactly this experiment. Here you see the images of the cells she selected and the corresponding graphs of the emission intensities and the Fred ratio. Initially she waits some time until the signal gets to a stable baseline. Then she adds the stimulus. Here a mix of 25 micromolar forskolin and 100 micromolar IBMX to maximally elevate the intracellular CAMP concentration. Immediately after the addition, the Fred ratio drops. As this is a loss of Fred sensor, this drop indicates the increase of the intracellular CAMP concentration. After the Fred ratios reach a new plateau, the experiment is done and we can move on to the data analysis. Start the Metaflow program. As for analysis, the camera might not be switched on. Just confirm the popped-up error messages. Then load your protocol. Again, just confirm the message. Then open your experiment by pressing the respective button, navigate to your experiment and select the INF file by double-click. The experiment will load. You can now move through your experiment by either dragging the slider, clicking the forward or backward buttons, or with the arrow keys of the keyboard. Usually, you should have done a final time reset when you started the real experiment, which you will see here in the event list. So we started here and the first image was taken at 0.58 seconds. Check if the display range of the ratio image is set to your preferred values. After that, make sure that all thresholds are set to off, except if you deliberately want the threshold. Then check if both channels are correctly superimposed with the alignment tool. Open Run Experiment and then Align Wavelength. Tick Align during playback in the pop-up box. Then look at your ratio image and align as previously explained until you see the least color fringes. Usually then your alignment should be as good as possible. As mentioned before, the alignment might not be perfect for the whole image. If you would like to analyze a second cell, you may need to do it in the second round after realigning for that cell. You can now close the alignment tool. Now look for a cell-free region where you can place your background ROI. The easiest way is to look at a bright field image you should have taken during acquisition. To draw the ROIs, go to the Regions dialog. This time we will draw the regions on a wavelength image, as here we can light up dim details much better just by using this slider. Drawing the regions works exactly as I showed you before. Again, first draw the background region. Then use the polygon tool to create a more specific region around the cell. As long as you have a decent signal-to-noise ratio, and you are only interested to see the whole cell CAMP change, you can create the area quite roughly. This has the advantage that even if the cell would move or change their morphology a bit, it wouldn't leave the ROI. And as the background will be later subtracted, it will not influence your measurement significantly. However, if you would have to analyze details with just a few pixels, like this dim little tail here, you should draw your ROI as exact as possible. Otherwise, background noise might influence your measurement significantly. In this case, you will also have to pay attention to movements and if necessary to move the ROI during the analysis, which can be done by simply clicking on it and move it with the mouse. As we are not interested now in this tail, we can delete this ROI by right-click and choose Delete Active Region in the pop-up menu. If all ROIs are created, we can return to the main program. Don't forget to bring the increased brightness back to a normal level. Usually we are doing all mathematical operations in Excel or OpenOffice. However, as we are analyzing now, and this will not influence the already acquired images, you could also do some operations in the MetaFlow program. Especially if you want to export ratio images for documentation, it might be quite handy to subtract backgrounds or shadings. Open Run Experiment and then Reference Images. In the pop-up dialog, you can specify that you want to subtract a region and the number of this region. Do the same for the second wavelength. Now tick this box. That's it. Now close the dialog. By loading the next image, you will realize the difference. Because now the background is subtracted from the signal, the ratio changes significantly. However, as I would like to show you some basic operations like background subtraction in Exle, we will now switch back to non-subtracted images. Run Experiment, Reference Image, untick, Close. Go back to the start. Now we will have to tick Log Data. This means that the averaged signal intensities of the ROIs will be exported into a text file. In case you have Exle installed, you can also directly export into an Excel sheet. By default, the program uses the name of the inf file you created during acquisition. It makes sense to keep this. Now Excel will pop up. Click on the MetaFlow window to foreground it. In case you wanted to save the ratio images, you could tick the Save Ratios option. This might be useful if you want to save specific ratio images for documentation or to create a movie sequence. We don't have the time to do this now, but you should know that there is such an option. Utilities, Play Movie from Disk. Now go to one frame before your starting point, otherwise the values of your first image will not be saved, and click Forward. The experiment replays, thereby extracting the values of your ROIs. Here you see again the differential reaction of both fluorophore emissions to the addition of the stimulus. As expected, yellow goes down, whereas the cyan emission goes up, leading to a significant decrease of the Fred ratio. When the run stops, bring Excel to the foreground. Here you see all the main information. The time at which the image was taken during the experiment and the average fluorescence intensity of your region of interest in terms of gray values. Here for wavelength 1, which in my setup is the yellow emission, and here for wavelength 2, the cyan emission. The region is indicated by the number here. R1 means region 1, R2 region 2, and so on. The column here gives you the, in this case, non-subtracted ratio. Save this Excel sheet for further analysis. In case you do not have a compatible program to directly export these values, you can still open the log file with any other spreadsheet program that imports text files with comma-separated values. The final analysis will then be done in your preferred spreadsheet program. Here I will show you the main operations in Excel. First we will subtract the background for the yellow, then for the cyan channel. It makes sense to create a graph of these data to see if everything went well in the experiment. Here you can easily see that the sensor and the fluorophores reacted as expected. As soon as we applied our phospholin, the yellow emission decreased, whereas the cyan emission increased. Now we will create the ratio just by dividing the value of the cyan by the value of the yellow emission. This inverts the data and leads to increasing ratio values at increasing CAMP concentrations, which can be seen in the corresponding graph. Finally, we will create the Fred change graph. First, we will have to find the value for our baseline, which will be used to normalize all our data. Usually, you should use an average of 5 to 10 ratio values just before the application of your stimulus, which in our experiment is at about 450 seconds. Then you apply the shown formula, which in Exle is written like shown here. Create a graph of these data, as we will use it to analyze the experiment. If your curves would show nice plateaus before and after the stimulus, you would just subtract the Fred value before addition of your stimulus from the maximal Fred change, which would give you the stimulus-induced Fred change. However, here we have an underlying constant increase. The reasons for such drifting baselines often are not clear, but it's a quite common issue, and we have to take it into account if we want to calculate the Fred change induced by our stimulus. The easiest way is to extrapolate the drift graphically. Magnify the graph and create a line which you fit to a region of the curve before you applied your stimulus. Then copy the line and fit it to the maximum without changing the angle of the line. Now sum up the values where the lines cross the x-axis. That's it, we are done. The stimulus in our experiment caused a Fred change of 108% compared to the initial ratio value. In this way we can compare the answers of sensors to different stimuli or inhibitors and draw conclusions about their impact on cAMP levels or regulation, or explore their impact even on a compartmental or macromolecular level by using targeted sensors. To mention only a few, apart from cAMP sensors, there are also Fred sensors for cGMP, pK activity, calcium, pH or redox monitoring available. All this monitoring can be done in living cells and in real time. This has made Fred imaging a versatile and indispensable tool for the exploration of the multitude of intracellular signaling pathways.
I hope you've enjoyed this podcast on Fred imaging. And at this point, I would like to thank Professor Manuela Zaccolo and her team for helping us to make this happen.